So we were discussing about the Bernoulli's random variable, okay, and in the last lecture you remember that I have already described the equations for the Bernoulli's random variable as like this. Okay, this is the equation. So we will continue our discussion on it. So we have a problem. So in this problem is related to the error correction coding. That means you have a communication transmitter and there is a channel, maybe a wired channel or a wireless channel, and you have a receiver, okay, and the channel can introduce an error of the probability of error of the channel is 10 power minus 3. Then what is the meaning of this? If it sends on an average that's on an average, we can say there will be 1 out of 1000 bits, 1 bit out of 1000 bits may be error. That is the meaning, okay. That means 1 over 1000 is 10 power minus 3, okay. Now the transmitter transmit each information bit 3 times. This is the very important point. Your transmitter, suppose if the transmitter is having 0 1 0 1 1 like this, then this guy actually will transmit this 0 3 times, 0 0 0. After that this 1 will be transmitted 3 times. This is what happening, okay, this is what happening. So you can see each bit will be transmitted 3 times. Why? In order to improve the reliability, okay. Now so if it want to transmit 500 bits, then he have to transmit actually 1500 bits, because each bit will be transmitted 3 times. Now, and a decoder is majority vote to the a decoder takes a majority votes to the received signal. Suppose you have the received signal, suppose you have transmitted 0. That means you transmit 0 3 times, 1 2 3, and the receiver actually it receives something like for example it receives 0 0 and 1. Then actually it will take the majority is 0, so it will assume that original bit is 0. But if it is 0 1 1, then it will take actually majority as 1, then actually but the original was 0. That means this is an error actually. So it is we can expect an error if there are if the majority vote is wrong actually. So and find the probability that the receiver will make the incorrect decision. So this is the question, find the probability that the receiver may take the incorrect decision. That means let us assume that k is the number of bits, k is the, we can I will use a different color. Let k be the number of bits that the receiver can take the wrong decision, okay. That means the receiver cannot correct the receiver can correct actually only one single error. If there are more than that, actually it cannot correct it. So what is the error? Okay, so k is the number of bits that may be marked as a wrong decision, okay. KBB, the number of bits that can be marked as a wrong decision. That means if we have a wrong decision, the probability that k greater than or equal to 2, that means you can see in this case, you can see it is a wrong decision, and what is the probability that it can be 1 1 actually. The original transmitted signal was actually 0, it was transmitted 0, but 0 has been transmitted 3 times, 1 2 and 3 times. But you can see that what is the probability that may be marked as a wrong decision. then what is the probability? That means you have the probability of error for 1 bit. Okay, you have the probability of error for 1 bit. We will say this, I can say like probability of error for 1 bit is 10 power minus 3. Okay, and what is the, that means out of the 3 bits, out of the 3 bits I have a wrong decision. That means, what is this meaning? That is out of 3 bits there, what is the probability? What is the probability that 2 may become error? Okay, or erroneous. Okay, erroneous. So you can see here the probability that k greater than or equal to 2 means, what is the probability that out of 3 bits, that means I can choose 3 bits out, I can choose 2 bits out of 3 bits, that means 3 choose 2, and I have an error, it should be error, that means 2 should be error. Okay, both are independent. Anyway, I told you these are all Bernoulli trials. So, and other may be a wrong decision, that means correct decision. So this is the wrong decision, wrong, 2 are wrong and 1 is correct. Okay, so this is the probability that k greater than or equal to 2, but this is not complete. The problem is sometimes we have to take into account about the case where all the bits may become error. So or means plus. Okay, this multiplication is showing and, that means 2 error and 1 correct decision. So the total actually error may depend upon, so the error may depend upon 2 errors and 1 correct decision, or that is, this is what we have now explained here, 2 errors and 1 correct decision, and it can happen in 3 choose 2 ways. That's why, that is 2 wrong decision. Whenever there are 2 wrong decision, it is coming from the probability of the error. Actually, this is probability of error square into 1 minus probability of error. Okay, that is the correct decision. Now 3 may be error, that means 3 choose 2, or you can say that all 3 are error. Okay, that means I can say like this, 3 choose 2, not choose 2, out of 3 all are error, that means error cube. Okay, this is the idea. Now I can find what is the probability of error by just simplifying this. The probability of k greater than 2 is nothing but 3 choose 2 is 3 factorial by 3 minus 2 is 1 factorial into 2 factorial. Okay, and the probability of error is 0.001, it is 10 power minus 3, so square into 1 minus 0.001. Okay, this is the first part, that means 2 error and 1 correct decision. Okay, then plus 3 choose 3 is 3 factorial by 3 minus 3 factorial into 3 factorial. 3 minus 3 is 0, 0 factorial is 1. Actually, don't forget this is 0 factorial which is equal to 1 into 0.001 the whole power 3. So this is the final answer. So this is coming from, actually all three are errors. So if you get at least 2 errors, or if all 3 are errors, then the complete transmitted then the decision from the received signal is completely error. Okay, if you are getting 1 error, there is no issue, because I told you if there is only 1 error, in this case you can see if there is only 1 error, actually you can get the original bits as 0 because the other two are 0, so it will take the majority. That is how the receiver is designed. So you can see here, this is how we can use the idea of probability theory in finding out the bit error response of the system, okay, of a communication system. Next we will consider a problem, an example. A coin is tossed 10 times. Okay, you have a coin which is having a sample space, actually head and tail, and it has been tossed 10 times. Then what is the probability of getting exactly 6 heads? So what is the meaning? So you have tossed a coin 10 times, and you should get what is the probability of getting at exactly 6 heads? That means exactly 6, I am going to write the answer. Exactly 6 heads means other 4 should be tail, right? So there are 6 heads, you should get 6 heads. That means if P is the probability of head, then the probability of tail is 1 minus probability of head, right, in each trial. In each trial, this is the idea that we know this thing, okay, this is the basic idea. Now we should get exactly 6 head, then other means all other are tail, and that should be 4, okay. And this can happen in how many ways? There are 10 tosses, and out of that you need 6 heads, so you can have this can happen in 6 different 10 choose 6 different ways, okay. So this is the probability of exactly 6 head. So probability of 6 head is nothing but this one. So this you can write like this: 10 choose 6 into probability of head 6 into 1 minus probability of head raised to 4, okay. And this is nothing but a binomial distribution. Binomial distribution, as I told you. So this is how you can calculate. Anyway, this 10 choose 6 is 10 factorial divided by 10 minus 6 is 4 factorial into 6 factorial into probability of head. Usually the probability of head raised to 6 into 1 minus probability of head raised to 4. So this is how you can calculate it. You can do this calculation, okay. I hope this is clear to you. Next topic is the random variable. So what is a random variable? So this is the definition I am going to give you. So a random variable, you can see here, the random variable is a function that assigns a real number x of zeta. Usually this is known as zeta, okay, we will call this as zeta. So it is a real number which will assign it is a function that assigns a real number to each outcome. That means the outcome is represented by zeta in the sample space of the experiment, okay. So this is the basic definition. So this is what the random variable. That means I will give an example, then it will be very clear to you. Suppose you have a example of tossing a coin, okay, and the sample space you can expect is head and tail, and you know the probability of head is 1 over 2 in an unbiased coin, and the probability of tail is also 1 over 2, right? Now I am going to define a function. X of zeta, zeta. Here zeta can be either head or tail or, okay, or the yes, this is the sample space, so it can be either head or tail, okay. So you can find here, if so, suppose one person is standing here and E is assigning a value to the head. If it is head, E actually take a number 2. Okay, he assumed that you have got a number 2, and if it is tail, he is assuming that he is mapping to a number maybe 2.5. Okay, then you can say that x of head is nothing but, he is talking about 2, the number 2, it's a real number, and x of tail means he is assigning a number which is 2.5. That means if he is having a if he get a head during the experiment, he assumes, or he will write down a number 2, and if he is getting a tail, he is assigning a number 2.5. That means for the head he is assuming a number, he is assigning a number 2, and if for the tail he is assigning a number. It is up to our application. Okay, according to our application we can do like this. So then what is the probability of 2? Can you tell me? It is nothing but the probability of x of h. That's what it is, nothing but the probability of h, right? It is nothing but 1/2. Similarly, the probability of 2.5 you will get the same way. It is nothing but the probability of tail, and it is again 1/2. So this is what the random numbers, random variable. So this 2 and 2.5, actually this 2 and 2.5 we will call random variable, and the probabilities of each random variable is nothing but, it is given here, right? So you can see here, whenever you have a sample space, for each outcome you can assign a real number. That means let's say this zeta is the outcome, and to this outcome we can assign a real number. Here for the outcome head I have assigned a real number of 2, and for the tail I have assigned a real number of 2.5. Okay, then I will get another sample space. This sample space is nothing but, it is xx. You can see it is a random variable. It is a sample space of random variable. Okay, it is a sample space of random variable, and the probability of this random variable will be directly depending upon the original random variable or the original outcomes. Okay, sorry, original outcomes zeta. Okay, so this is what the random variable. So we will see an example. Yeah, we will see an example. Okay, so you can see an example 3.1 from the textbook, and this example, actually in this example you can see a coin is tossed 3 times. So a coin is tossed 3 times. So you know that these are all the outcomes. We may get either all head, maybe head, tail, all these things. Okay, there are 8 outcomes. You can see there are 8 possible cases. 1 2 3 4 5 6 8. Okay, 8 possible cases. How you are getting this 8? 8 is nothing but 2 power 3, because you are tossing a coin 3 times, and in each time actually you may get either head or tail. So it is 2 power 3, and I am assigning, if it is 3 heads, that means if all are 3 heads means h, then I am assigning a random variable x of h is nothing but 3. That means I am just counting the number of heads. So here I am assigning a rule counting the number of heads. Okay, I can also make a rule such that I can count the number of tails also. That is also possible. But here you see in the previous example, I am assigning a number 2 for the head, and I am assigning a number 2.5 for the head. That means whenever we are talking about the random variable, all the outcomes will be mapped into a real number, and my sample space of the random variable will be always a real number. Okay, we are talking about the real number. Okay, it can be complex also, that we will discuss later. So if it is 2 heads, That means I can have many cases, head, head, tail, or can be tail, head, head, or can be head, tail, head. All these three cases I can have. That means the three heads means not three heads, two heads means two heads. So x of two heads is that means I am saying my random variable is 2. Okay, so here previously 3 heads means my random variable is 3 and 2 heads is random variables is 2. Okay, so the random variable is 2. Like this I can have a sample space as shown. I can have 3, so I can have 0 heads also. 0 heads means I can have the same thing, I can have it's 0. Similarly 1 head means I can have a random variable 1. I can have a random variable 1. Now what I want to say is that my sample space of the random variable, so these are all the random variable, my x, these are all the random variables. So my x have the sample space, that means x is the random variable. I have already told you x is the random variable. So the normal notation for the random variable is x. So this is what I want to tell you. The normal notation for the random variable is x. So my sample space for the x means I can have 0 heads, 1 head, 2 head and 3 head. Okay. And in the previous example, you know what is the sample space of the random experiment. It is nothing but I can have either 2 or 2.5. Okay. So this is how we can define a random variable. So it is a according to, for each outcome we are going to map it to a real number. So this is my sample space. Okay, so this is how we can define the sample space for the random variable. This is the random variable. So I hope this is clear to you. This is how we can define it. Okay, now we will see the discrete random variable and their probability mass function. Okay, so how we can assign the probability mass function for the discrete random variable. So in the previous the discrete random variable x is defined as a random variable that assumes a value from a countable set. That means you have a countable set xx. Okay, so as I told in the previous example of tossing a coin, then the sample space xx means 2 and 2.5 in the previous example. That means if it is head, I told you I assign a value 2, and if it is tail, I assign a value 2.5. So this is my sample space. Okay, and this is a countable set. You can see that it is a countable. The number of elements, actually it is countable. We can count the number of elements. Okay, so this is the case of a discrete random variable. It is a countable set. Okay, that means you can assign a natural number to each and every outcome in a of the random experiment, okay, or the random variable. So you can see here a discrete random variable is said to be finite if its range is finite. That means you can have the random variable, as I told you in the discrete random variable, it can have the elements like x1, x2. So in this case you can see you have only x1 and x2, but in general you can have x3 also, you can have x4, it will continue, okay, like this. But you can assign a real number. That means this is the first element, you can say second element, you can say third element, like this. You can assign, this is the fourth element, you can assign like this. It is not actually uncountable, actually it is countable, because for each element, countable means for each element you can assign a natural number. Okay, this is possible. But if you take a real line, the number of points on a real line is not countable, because if you take a point 1.001, then very near to that point maybe 1.0011 is the next point maybe, but also you can find any point in between also. So you can not assign a natural number to the real line, okay, for each element in the real line. But there are some cases here. Now what we are defining is a discrete random variable is defined in such a way that your random variable x, your x is a random variable, and it contains many elements, infinite number of elements will be there, but for each element you can assign a real number. That's why it is countable. Okay, now we will talk about what do you mean by the finite. Okay, that means what do you mean by the finite discrete random variable. RV means discrete random variable. That means if you have a sample space like this, x1, x2, etc. up to xn, that means the number of elements is limited. The number of elements n is less than infinity, you can say. If this is the case, then we will say it is a finite discrete random variable. Okay, that is finite discrete random variable. But if this is the situation, this is the general situation, it is not finite, it is infinite, but the set is countable. The set is countable. It is infinite but countable. Okay, countable means for each element you can assign a real number. If it is not countable, then it is not coming under the class of discrete random variable. It will comes under the class of continuous random variable, that we will discuss later. Okay, so that's about the discrete random variable. Okay, it's finite, and infinite is also possible. Infinite means it is countable. Okay, finite is also countable, infinite is also countable. But even though if it is the number of elements is infinite, okay, in the sample space, you can assign a real number to each element. But in finite case, the number of elements is is finite. So I will give an example for this. So tossing a coin, I told you the tossing a coin, that means I have a sample space which is head and tail. Okay, but I am defining a random variable sample space here. This is the sample space of random variable. What is my random variable? Here x is my random variable. Okay, capital X is used to denote the random variable in general. So what are my random variable? If I get the head, I am mapping it to a point 2. If I am getting a tail, I am saying I have 2.5. And what is the probability of this? The probability of 2 is nothing but your probability of head, because 2 is coming directly according to the head, so it is 1/2. And the probability of this guy of 2.5, it is directly coming from the tail, so it is again 1/2. You can see that there are only two elements. So you can count the number of elements also, and it is finite. So it is a finite discrete random variable. So this is the finite discrete random variable. Okay, so this is one of the example. Similarly, in the previous example, as I discussed in tossing a coin, this one, it is also a finite discrete random variable, because you can see the outcomes are finite. The outcomes are finite, so it is a finite discrete random variable. Okay, that's it. But the probability of 0 means no heads. So that means it is nothing but you can directly calculate according to the Bernoulli's distribution that we have already discussed before. Okay, so this is the finite discrete random variable. Now there is an important concept for the random variable, that also we will discuss. Similarly, tossing a dice. Okay, this is an example, another example, tossing a dice. So the outcomes are directly random variable anyway. The outcomes are 1, 2, 3, 4, 5, 6. Okay, it's random variables, and each one is having a probability of 1 over 6. That means all outcomes, that means the probability of all outcomes are 1 over 6. Again, this is a finite random variable, that means finite discrete random variable. Discrete random variable. Okay, again it's a finite discrete random variable. So the number of elements in the sample space are countable. Okay, the number of elements are countable. But if you take a real line, if your sample space xx, if the sample space xx is a real line between 0 and 1, that means you have a real line between 0 and 1. What is the meaning? You have infinite number of points between 0 and 1, and for each point, is it possible to assign a real number? No, is it possible to assign a natural number? If you take any point here, for example, any point x here, you can see very closest point, let's say x1, but in between x and x1 you can see another point, right? So it's not possible to assign a real number to each and every number in the whole sample space. So this is a continuous case. Okay, this is a continuous random variable that we will discuss later. Okay, now I want to tell you what do you mean by the probability mass function of a discrete random variable. Probability mass function of discrete random variable. It is associated with a discrete random variable. The same thing associated with the continuous random variable is known as probability density function. Okay, but here it is the mass. Why it is mass? Actually, we can discriminate each and every point. That's why it's a mass function. So probability mass function of a discrete random variable x is defined as px of x. You can see this equation is nothing but the probability of x equal to x. Okay, for a real number. So don't worry by seeing all these definitions. It is nothing but just the probability of each element in the sample space. So let us consider an example. Okay, tossing a coin, xx, tossing a coin, okay, tossing a coin, you can say tossing a coin, then you have a sample space which is head and tail, and you are defining a function. Define a function. Head means I will note it as 2, and my tail means I will note it as 2.5. then that is my mapping. Okay, this is my mapping x of zeta, where zeta is each outcome, x of zeta. Here zeta is head and here zeta is tail. Okay, so what is my random variable? Xx having this, my random variable xx is having a sample space 2 and 2.5. Okay, now this has a probability. Okay, the probability of the random variable x is equal to 2 is nothing but half, because it is directly coming from the head. That's why the probability of head is actually, since it is coming from the head, the probability is half. Okay, similarly this one, the probability of x, the random variable x, which takes the value 2.5, is again half, because it is same as that of the probability of tail. So this thing, whatever we are describing now here, I have shown in the boxes, this is nothing but the probability mass function. Probability mass function. The probability mass function. Okay, so this is known as the probability mass function. That means for each outcome zeta, that means each outcome zeta, x of zeta is equal to the value x, then it is nothing but the probability mass function. So the probability mass function is usually denoted using this notation. Okay, the probability mass function is usually denoted using this notation. So probability mass function of the random variable x is nothing but the probability of the random variable x which takes the value small x. That means the probability, this is nothing but it is nothing but the probability that the random variable x takes the value small x. We can also denote like this: x takes the value small x. So all are same. Okay, this. So this is nothing but the probability mass function. Okay, I hope it is clear to you, right? Now what I have shown here, if you have a sample space, then I am mapping each set A1, A2, I am mapping each set A1, A2, A3 to a real number as I have shown. Then I can represent the probability distribution of that random variable like this. That means the probability distribution can be denoted as the probability of that random variable along with the probability mass function. So I will give an example for probability distribution function. So what do you mean by the probability distribution function? That's what we are going to explain. So you have a random variable x which takes the value x1, x2, etc. Okay, or in general you can say xk. In general xk are the values. Then the probability of that random variable which takes the value xk is nothing but the probability mass function. Okay, now I can, so this is the probability mass function. That means for each xk I have a probability mass function, right? So the set, this thing I can denote like I have each set, each xk, I have a probability mass function p of xk. So this set we will call it as the probability distribution function. Okay, it is nothing but the probability distribution function. I will use the capital letters, all the capital letters. Okay, probability distribution function. Okay, this is known as the distribution function of the random variable. Now we will see an example. Let us toss the coin. Tossing the coin. Let's say the sample space for tossing the coin are head and the tail, and for the head I assign a value 2 and for the tail I assign a value 2.5. so this is known as a function, and this function is will give you the random variable. Okay, so you will get a random variable by assigning this function. You will get a random variable. What are the random variables? You will get a sample space of random variable. This is the sample space of random variable x. It is nothing but 2 and 2.5. Okay, and what are the probabilities of this guy? The probability of 2 is, x is the random variable, so the probability of 2 is half, and this is, x is the random variable, and 2.5 is an outcome of this random variable. Again it is having a probability half. And how this half is coming? This half is coming from the head and this half is coming from the tail. Okay, so this is the random variable. Now what is the probability mass function? You can see this is all the probability. So these two are called the probability mass function. Okay, these are all the probability mass function or PMF of the random variable. Now I will talk about the whole distribution, that the probability distribution function. What do you mean by probability distribution? PDF. What is it? It is nothing but I have the value 2, and what is the probability? The probability is 1 by 2. I have the value 2.5 and the probability is 1 over 2. So this is nothing but the probability distribution function of the random variable. Okay, this is the probability distribution of the random variable. It is not the probability distribution function. Sorry, I have made a mistake here. It is not the function, it is the probability distribution of the random variable. It's not PDF, it's a probability distribution. Okay, probability distribution function is different, that we will discuss later. So this is nothing but the probability distribution of the random variable. But what do you mean by this PMF? I will explain. You know this. The PMF means probability mass function. Mass function. So what is this? It is nothing but the probability of x takes the value xk. Okay. Now the probability distribution means it is a set. We can say it is represented like this. You have the xk and its probability mass function. Okay, this is the probability PMF. Okay, mass function of that random variable. This is the probability distribution. Okay, now it is having certain properties that we are going to discuss now. PMF will satisfy some of the properties. The probability mass functions, the PMF will satisfy some of the properties. We have seen that it is a probability, so the PMF will be always greater than 0, right, or equal to 0, maybe 0 or greater than 0. It will be always a positive number. That's it, right? It is a positive number below less than or equal to 1, right? Less than or equal to 1. Less than or equal to 1. That is the main important thing. Okay, it can be equal to 0 or greater than 0, but it is less than or equal to 1. And if you add all these elements, if you take our previous example of tossing a coin, if you add all these mass functions, then you will get 1. For example, let us assume that tossing a coin with head we assume 2 and with tail we assume a value is 2.5. okay, then the sample space of the random experiment is 2 and 2.5, and the probability of this, the probability is 1 by 2 and this probability is 1 over 2. Now if I add the probabilities, if I add all this probability, I will get 0 or 1. It's 1, right? So we will get 1. Okay, that means it is less than or equal to 1, or everything is greater than 0. You see, it's greater than 0. This is also greater than or equal to 0. Okay, this is the first point. And the second point is, if we add all these things, we will get 1. So this is our second point and this is our first point. Okay, now if you take the subset, this is what the next point. That means third point, if you take a subset, let us assume that a subset B is equal to only 2, then the probability of the random variable x in B is nothing but you take only the x which corresponding to 2. It is nothing but 1/2. Okay, so that means it's a very straightforward thing. You can see if B is the subset of, you can see here B is the subset of sample space, B is the subset of sample space XX, and what is our sample space? It was 2 and 2.5. So if you take only one element, then, or if you take two elements, then you have to sum up. If you take only one element, you have to, but here in the sample space there are only a total of 2 elements. So we can take only one element or 2 elements, okay, if it is a subset. So that's what the main point that I want to tell you. Okay, so we have an example which is 3.5 from the textbook. Okay, you are causing a coin 3 times. Okay, and you are counting the number of heads, that is counting the number of heads. Okay, so if you get all the tails, then you know that this is a random variable 0. That means your random variable can take the sample space 0, 1, 2 and 3, and all 0 means the probability I told you 1 by 2 power 3, because all should be tail. Now 1 tail means that we have already covered this problem. You can see this is the probability. Similarly 2 heads, this is the case of one head, then this is the case of 2 heads, and this is the case of 3 heads. Okay, so you can get it as the probability of 0 you will get as 1 minus p cube. That's what I want to tell you. So where p is the probability of head, it is the probability of head. So what is this probability? This is nothing but p cube. And what is this probability? It is nothing but 3 times 1 minus p the square into p. This we have already solved in the previous just before some few hours. Okay, so this is again you know 2 heads means 3 into 1 minus p into p square. Okay, and 3 heads, so 3 heads means p cube. Okay, so this is the probability mass function of 0, this is the probability mass function for 1, and this is the probability for probability mass function for 2, and this is the probability mass function for this is the probability mass function for head. Okay, all head, 3 heads. Okay, so this is nothing but all are PMF. Actually these are all PMF. This is the probability mass function. Okay, so we can represent this mass function in a different way. We can show it in as a graph. We can show it as a graph. Then for 0 I can say what is my y axis? It is nothing but 0 means 1 minus p the whole cube, right? So it is not the p cube, it is 1 minus p the whole cube. Okay, I think I have a whole cube. Okay, 0 head, so 0 head means 1 minus p the whole cube. Okay, now this is my first one. Then for 1 I have actually 3 into 1 minus p the whole square into p this. Next all this set, next it is 2 is the element, the PMF for that is 3 into 1 minus p into p square, and the fourth element is 3, and for that it is p cube. Okay, so this is the distribution function. This is the distribution, not function, this is the distribution, probability distribution. So the above one is the probability distribution. But there is one more thing, which is the probability distribution function. That means that we will discuss later. So the probability distribution function I can represent like this: 0. Suppose if I am considering if the probability of head, that means your p of head is equal to 1 over 2, then I can say that my distribution is, the probability distribution is, I have 0, then 1 by 2, it is 1 minus 1 by 2, that means 1 by 2, 1 by 2 cube is 1 over 8. So this is coming from 1 minus 1 by 2 whole cube, which is nothing but 1 over 8. Similarly, you will get the second element is 1, and 1 has 3 into 1 by 8, that means 3 by 8. You will get it is, this is coming from 1 minus 1 by 2 the whole square into 1 by 2. Okay, this you will get it as 1 by 8. Then you have to multiply with the 3, so there is a 3, so 3 by 8. Okay, so 3 by 8. Similarly, I will write it another one also. It is again 3 by 8. Okay, again 3. For 3 it is I think 1 by 8, right? This is, so this is nothing but the probability distribution. So we can show it as a graph. You can say it as a graph, okay, of a probability mass function. You can say it is a probability mass function graph. So this is the probability PMF as a graph. For 0 you have 1 by 8. Okay, I will use 1 by 8. Okay, and for 1 you have 3 by 8, 3 times of it, 3 by 8, and for 2 you have again 3 by 8, and for 3 you have 1 by 8. So this is nothing but your probability mass function. So this is your random variable x, okay, and the y axis is PMF. Okay, the y axis I will denote in another way. So this is the x axis and y axis. So this is the PMF. And what is this? It is the Px of x, that is the y axis. So this is known as the probability mass function. So this set we will call it as probability distribution. Okay, next we have an important topic which is known as the cumulative distribution function. So what I want to tell you is that we will continue with the same example. So let us assume that we have the same example. I will consider the same example before. The distribution was something like this: 0, for 0 it is 1 by 8, and for 1 it is 3 by 8, and for 2 it is also 3 by 8, and for 3 it is 1 by 8. Okay, this was our distribution. Now can you tell me, and our sample space was xx as 0, 1, 2, 3. Okay, can you tell me what is the probability that the random variable x takes the value less than or equal to 0? What is that probability? It is nothing but, you see, there is only one outcome which is related to 0, and before 0 there is no element which is less than 0 in the sample space. You can see the sample space is starting itself with 0, right? So there is no element which is before 0 which is less than 0. So our definition is giving you something like, it is giving you less than or equal to 0. So there is only one probability which is associated to that. There is nothing previous. It is nothing but the probability of x takes the value 0, right? Am I correct? And it is nothing but 1 by 8. Can you tell me what is the, so what I can represent in graphically? So I have this one. So this is my 1 by 8, and this is my 3 8, this is my 3 by 8, this is my 1 by 8, and this is my 0, 1, 2, and 3. Okay, and this is my probability mass function. Now I am asking this question. So how we can, you can see what is the probability that the random variable, this is your random variable x, okay, this is your random variable x that takes the small value is the random variable x, which takes the value small x, okay. Now if you consider the probability of x less than or equal to 0, means you have to take all the values whatever before 0, and you have to add all these probabilities till you reach 0. But when you reach, you can see here if you consider any point 0 minus, okay, that means the probability that x less than 0, that means I am not including 0, not including 0, then what is that? There is nothing in the sample space which is less than 0, so that probability was 0. That you should be very careful. But when I talk about the probability that x less than 0, what I am doing, the probability that x less than 0 plus the probability of 0. You see here the probability that x less than 0 was 0 and the probability of 0 was 1 by 8. So, I will get this number as 1 by 8. Now, I can also define another thing. What is the probability that x less than or equal to 1? It is nothing but the probability that x less than 0 plus the probability that x equal to 0. I can write like this, x equal to 0 plus I want to reach till 1. I have to include 1 and I want to take all the values before 1. That's why I have taken less than 0 and equal to 0. Then what I am doing, the probability that x less than 1 and greater than 0, that means x is greater than 0 and not equal to, this x is between 0 and 1, then I have to take the value which is x equal to 1 also, right. That means there is nothing here between 0 and 1, there is no value in between 0 and 1, it is 0. That means this part is 0 because there is nothing here on the y axis. In the x axis nothing is the y axis nothing is defined for this portion. It is because we are talking about discrete random variable. When we talk about the continuous random variable, we can expect the values between 0 and 1, all the values between 0 and 1. So, here that is 0, but when I talk about x is equal to 1, that means I have to take only this value, right. This value x is equal to 1, it is 3 by 8, and at x is equal to 0, you already know it is 1 by 8. So, the probability that x less than or equal to 1 means you just need to sum of the first component is 1 by 8 plus you have to take only 3 by 8. Okay. So, you are considering this 1 by 8 and 3 by 8, then you are getting 4 by 8, this is 1 by 2. And this kind of definition, that means the probability that x less than, the probability that x takes the value less than or equal to some random variable xk, this is nothing but the cumulative, this is known as cumulative distribution function. Okay, this is the distribution function. So, this is the cumulative distribution function of the random variable x of x, takes the value xk. Okay, this symbol is denoting takes. This symbol is nothing but it takes the value xk. So, this is what the cumulative distribution function. Now, you can easily define what is the probability that x less than or equal to 2. The probability that x less than or equal to 2 for the above example is nothing but probability that x takes the value equal to 0 plus probability that x take the value equal to 1 plus probability that x takes the value equal to 2. Okay. So, this is 1 by 8 plus 3 by 8 plus 3 by 8, that is it. So, this is nothing but the cumulative distribution function CDF. So, we will call it as CDF of the random variable, cumulative distribution function, okay, CDF of the random variable. This is very important concept in analyzing the analyzing and modeling the stochastic engineering systems. Okay. So, we will see what are the properties of this cumulative distribution function in detail. Okay. So, cumulative distribution functions will be explained in detail. So, do not forget this concept. So, the cumulative distribution function that we have seen that the cumulative distribution function is of a random variable x is defined as the probability of the event x less than or equal to x. Okay. So, I can also represent it like xk also, there is no issue. So, this is the notation for this. I can represent it the same thing in another way also, fx of xk or x, or I can represent x also. Okay. So, fx of x, so this is more general, fx of x is more general. Okay. So, fx of x is nothing but the probability that the random variable x takes the value less than or equal to small x. Small x is the value of the random variable, and x is denoting in general the random variable. So, this is your x can be, for x can be varying from minus infinity to infinity. X can take any value between minus infinity to plus infinity. Okay. So, what are the properties? The first property, this is the first property, is very important. The first property is nothing but it has a value which is always less than or equal to 1. It is a value which is less than or equal to 1. So, from the previous example itself, you know all these values in the previous example. For example, it is 7 by 8. 7 by 8 is basically it is less than 1, because when you talk about any value, what about for example, what is the situation for x less than or equal to 3? It is nothing but 1 by 8 plus 3 by 8 plus 3 by 8 plus 3 by 8 plus 1 by 8, which is again 1. Then what is the probability that x less than or equal to 4? It is again 1. You see here, it is again 1 here. Why? Because the value is not increasing, because there is no element after 3. So, whatever you consider after 3, it has the probability as 0. So, up to 3 it was 1. So, if you consider any element after 3, the probability is 0, because there is nothing like that in the sample space. So, 1 plus 0 become always 1. So, what I want to tell you is that the random variable, this cumulative distribution function is very important concept in random stochastic processes, okay, in stochastic processes and all, okay, in defining the stochastic processes. So, the first property is it is less than 1, okay, or it is between 0 and 1, and if the probability of x is equal to 0, then x is not the element in xk, okay. The probability of x is equal to 0 means it is not the element in xk. For example, if you are tossing a coin, I told you the sample space was head and tail, and the mapping is nothing but is 2 and 2.5 in the previous example that we have considered, okay. Then if I take the probability of 2.25, what is the probability? It will be 0, because there is nothing like 2.25 in the above set. If you compare, this is 0, that is what the meaning, okay. Now, if you add all the probability, it is obvious that it will be equal to 1. So, the sum of all the probabilities, that means if you consider all the outcomes and add all these things, then the total probability will be equal to 1. So, that is the idea. Now, we will consider a example next. You have 3 coins which is tossing. So, the same example we will see it in a different way. So if you see that this if we see that okay, so we will see the same example in a different way. So there are three coins which are tossing, okay, which are tossing at a one by one. Then we will note down all the outcomes of the number of heads, okay, the number of heads as we discussed before. So as we seen that we have the random variable. In the previous example, actually we have seen the random variable is 0, 1, 2, 3, because we have 3 heads, 0 heads, 1 head and 2 head. Okay, these are all the cases, and it has the probability 1 by 8 and 3 by 8, 3 by 8 and 1 by 8. These are all the corresponding probability or probability mass function P x of xk. All these are the probability mass function. Okay. Now I told you we can represent this probability mass function in a graphical way that we have seen. Okay. Now we can represent instead of probability mass function, we can use another idea. Okay. The probability mass function you have already seen how to represent. We can also represent the cumulative distribution function. So the cumulative distribution function x less than the cumulative distribution function is let me check I have made any mistake. Okay, it's fine. So the cumulative distribution function of 0 is nothing but the probability that the probability that the random variable x takes the value less than or equal to 0. It is nothing but 1 by 8. The cumulative distribution function of 1 is nothing but the probability that x less than or equal to 1. It is nothing but the probability mass function of 0 plus probability mass function of 1. That means you have to add everything till 1. Okay. Next is probability distribution. That means the cumulative distribution function of 2 is nothing but the probability that x less than or equal to 2. It is probability that x is equal to 0, or it's probability that x is equal to 1, or probability that x equal to 2. That means you have to add till 2. So the first case, this is 1 by 8. First case was 1 by 8. The second case was 1 by 8 plus 3 by 8. This is equal to 1 by 8 plus 3 by 8 plus 3 by 8. Okay. So we will get this as 7 by 8. Okay. And fx of 3, you know the probability that x less than or equal to 3 is nothing but x equal to 0, 1, 2 and 3, which is nothing but 1 by 8, 3 by 8, 3 by 8 and 1 by 8. So this is nothing but 1. So we can actually show the cumulative distribution function graphically. So that's what it has been shown here. Okay. So you can see here I have a cumulative distribution function CDF fx of x. Okay. And this is 0, this is 1, this is 2, this is 3. The probability that x less than or equal to 0 means, you see here I have represented, if x less than 0 means what? X less than 0, there is nothing less than 0. Okay, here up to this the CDF was 0, but at 0, x less than or equal to 0, at 0 till 1 I have the same value, which is nothing but 1 by 8. Now when I reach 1, I got the value which is 4 by 8. You can see 4 by 8. So 4 by 8 is here maybe. So this is 4 by 8. but this will continue only till 2. When I reach 2, I have the value 7 by 8. So, maybe here 7 by 8, and this is 7 by 8. When I reach the value 3, you can see it become 1. So, maybe here 1. Okay. So, I will just show for your convenience, this is less than or equal to 1. Okay. Like this I have to show little bit close to 3. Okay. This is okay. This is 8 by 8, which is nothing but 1. So, this graph, this kind of graph, we will, it is the graphical representation of CDF. Okay. So, this is the CDF fx of x. Okay. Now, you see here everywhere you see here this is a constant here between 0 and 1. Between 0 and 1 it is a constant, because there is no element between 0 and 1 in our sample space, because our sample space was 0, 1, 2 and 3. So, there was no element between 0 and 1. So, the probability assigned to all these things will be 0. That is what we have seen previously. If some element has a 0 value in the probability, then it means that it is not an element of xk, it is not the element of your sample space. Okay, it is not the element of your sample space.